Hey everyone, this is Mayur. Welcome back to MLWorks. In this video, we'll be discussing about embedding quantization. So first we'll understand what is quantization and then we'll talk about embedding quantization. So quantization is nothing but a way to reduce the size of your model. Okay, in general terms. For example, if you have a model which contains parameters in float 32 floating point numbers, then you convert that into int 8 or you convert that into float 16 or bf16, which will automatically reduce the size of your model by 2x or 4x. Okay, so that's what quantization is. So when it comes to embedding quantization, and embedding is nothing but a vector of floating point numbers. So this each floating point number is turned into quantized and it is turned into int 8 or binary value or something like that. Okay, so with that, we can understand here in this notebook itself. Okay, consider you have 50 million vectors, and each vector has 1024 dimension, and each value contains 4 bytes, consume 4 bytes. So it takes around 200 GB of memory to just load those vectors. Now, if you turn that floating point 32 to int 8 or binary, right, automatically the size of the whole memory requirement reduces drastically, and also the time taken to retrieve the embedding from your memory is also quite fast if you reduce the memory. Okay, with that in mind, let's get started with the notebook. So first, let's install the package sentence transformer and import the packages. One is sentence transformer and quantize embeddings. So let me run this. So here we are importing sentence transformer, some sentence transformer, and then from sentence transformer we are importing the module quantize embeddings. And then once that is done, what we do is we load the specific embedding model, which is from mixedbrid.ai. So once that is loaded, we'll look into what is called as binary quantization. So binary quantization is nothing but if you have float 32 integer or floating point number, we turn that into binary 0 or 1. So by that, what we do is we reduce the memory by 32x, because instead of consuming 32 bit, we are consuming only 1 bit to identify the information. So once we do that, what we'll do is once the embeddings are turned into binary embeddings from floating point numbers to binary numbers. Okay, so what we do is we compare the embeddings using Hamming distance. So if we look at here query, we have a particular vector of binary embeddings 0, 1, 1, 1, 0, 0. So we have some sample embeddings. We can find the distance between this query and this sample, and whichever is closest to it will be considered as the similar document. Okay. So in this case, if we see, the first dimension is matched with everything. Second dimension is matching with all the samples. Third dimension is matched with S1 and S3. Fourth is matched with none of the samples. Fifth is matched with S1 and S3 again. Last dimension is matched with all the other samples. So when we do the Hamming distance calculation, Q1 will be similar to S1 and S3. It will be the closest one. It is not similar. It will be the closest one. So with that, we are trying to retrieve the documents by reducing the size of the uh, each of those dimensions value, right, from float 32 to binary. So as it is given, lower the Hamming distance means closer the binary embeddings. So in this case, Q1 is closer to S1 and S3. So we'll try to implement that. So if we see here, we have our model.encode. We have already mentioned our model initialized here. So then what we do is we pass two sentences and turn that into an embedding. And then that embedding is, then we use something called as precision is equal to binary, turn that into zeros and ones. So let me run that. Now what we'll see is the change in the memory requirement, right? Let's look at that. So here we have embeddings and then we have binary embeddings. Then we'll have shape, n bytes, d type, and for binary embeddings similar to that we have shape, n bytes, and d type. So let me run this. So here we have two records. That's why we have two and 1024 dimension. Okay, each one record has 1024 dimension and each takes 4 bits. Okay, and 4 bits is equal to what is the calculation happening here is, if I go just type in here 4 into 1024 into 2. 2 refers to the 2 records, 1024 refers to the 1024 dimension, 4 refers to the 4 bytes. So this will result in 8192, which we see here, the total number of bytes. And D type is N32. Now, once we do with the binary embeddings, what we do is we turn this into 2 comma 128. So that calculation, how does that comes 128, right? So consider you have 1024 bytes. Okay, so we turn that into binary. So each binary will have one bit. So 1024 bytes is turned into 1024 bits. Now we normally represent in terms of bytes. So what we do is 1024 is divided by 8 and we turn that into 128 bytes. So these two records after binary quantization turned into 2 comma 128 bytes, and total size is equal to 256 bytes, and it is of type int 8. 0 and 1 are represented as int 8. So next, so this is with respect to binary quantization where we reduce the memory by 32x. So next we go to scalar quantization. So this is something similar to binary quantization, but much higher precision can be brought up with a little more cost and little more memory requirement. So what we do is first we convert float 32 into int 8. That int 8 can help us to map it to a value something in between 0 to 256, 255 or minus 128 to 127, which is signed integers. Okay, so the total requirement, memory requirement also changes. So for float 32, we need 1024 into 4 bytes. To changes to 1024 into 1 byte. Okay, so we are reducing it by 4. The size is 4. So what is happening in scalar quantization? So consider you have an embedding which has value between minus 2 to min and max. Min and max of the particular embedding is minus 2 to 5. So what we do is we map it to minus 28 to plus 27 or 0 to 255, which is our int 8 representation. Okay, that is, this is like up to us how we want to represent the value of that int 8. So what we'll do next is we have a data set here again. Okay, we'll use that data set. We'll encode the corpus. Okay, using some particular model, embedding model, and then we take in our two samples. And then what we do is using quantized embeddings, we pass in the embeddings that we have generated from here. Okay, and then we are giving the precision as int 8, and then we are giving the calibration embeddings as calibration embeddings here. This is the one, the corpus one. So what this will do is this calibration embedding is where you will find this min value. Okay, from the data set we'll get 1000 values we have per column. Okay, so from that 1000 values there will be one minimum, one maximum, and that will be mapped to minus 128 and plus 127. So that is our mapping of min max to a specific range. So let's run that. So here also we'll have embeddings shape n bytes d type, and similarly in date embeddings shape d n bytes and d bytes d types. So this is quite taking some time. Let's wait for this to cover. Let me run this as well. Also run this cell. So why it is taking time is because we have 1000 records and we are trying to perform embedding on each of those records, and then we are trying to do something called as quantization on top of those records. So that's why it's taking time. So this is done. It took around 36 seconds, and then we are able to get our int 8 embeddings. So earlier what we saw is shape is 2 comma 1024 bytes, which is again which we calculated earlier, float 32. And in this case, instead of 128, in 128 for binary, 1024 bytes. Okay, so in this case, it is bytes directly. We don't have bits, it is bytes here. So directly we have bytes. So 2 into 1024, 2048. Here 2 represents the two records what we have. And it is the type is int 8. So if we see here, one of the records of int 8 embeddings, it is ranging from minus 26. Okay, it's the value is ranged between minus 128 to plus 127. That is the range that we have given for this embedding scalar quantization that we have given. Now this is the way to reduce the memory of your embeddings. Okay, now what we'll do is we'll understand just the performance rate changes that happens once we do that. So retrieval speed, consider you are performing a RAG, right? You have a RAG system and you want to pull it from a vector DB. So if you do these kind of quantization techniques, then what we can see is we'll see the change in speed of retrieval. So if you have float 32, the speed is 1x, and then int 8 the speed increases by 3x, and mean speed increases is 3.7. The max speed that can go up to is 5x. Similarly, when you're using binary quantization, the speed goes up by minimum of 15x speed will be there. At least average speed will be 25x approximately, and maximum speed you can get up to is 46x. So that is the retrieval that happens, right? When you are retrieving a document from your vector DB, that could be improved if you store that quantization based embeddings in your vector DB. So this is with respect to retrieval speed, and there is performance speed overall. So what you see is here, when you have float 32 as embeddings of each of the dimension values, so you have, this is the performance. Okay. When we say performance also in terms of the quality of document that is retrieved, okay, that is also one of the performance metric. So when you have float 32, your perfect documents are picked out from your vector DB. So if you're using int 8 as your quantization, then you will, the performance will reduce by 0.7 percentage. Okay, and the retrieval speed will be increasing by 4x, and the memory and the index will be what, reducing, the memory will be reduced by 4x. So we are getting 4x speed at a cost of 0.7 percentage in terms of performance. And in binary, when we are doing it in terms of binary quantization, the memory and index size saving is 32x, and retrieval speed is increased by 45x, and the performance is degraded by 0.4 percentage. Okay, at the when you are losing 4 percentage of performance while retrieving the document, you are increasing the speed by 45x, you are reducing the memory by 32x. Okay, so there is a a leverage between what the performance and the retrieval speed and the memory that you can have, okay, that you can reduce, right? So these are like kind of uh, performance metric that you have to think about, like what is better, right? If you have less memory, okay, and you have if you want a quicker smaller latencies, okay, then you have to think about these quantization techniques and apply it on your embedding vectors. Okay, so with that, I'll be concluding this video. Thank you so much.